Good evening, everyone. My name is Rachit neema, IT-2K24-71. Today, I am going to present solution for assignment 3 for the subject numerical analysis and design taught by our professor, Dr. Sharira Pachapat sir. So let's start with the first question. The first question is to find roots for the equation x square minus x minus 1 equals to 0. By default, we know the roots for this equation is 1.618, but we are going to solve uh, for this equation using different iterative methods. So for the first method, we have bisection method. So what is bisection method? Bisection method is a method to find the roots of the polynomial. The geometric interpretation for the bisection formula is repetitive bisection interval a and b, where f of a dot f of b should be less than 0. Then we calculate midpoint m equals to a plus b divided by 2 and replacing the endpoint with the same sign. Root trap is in successive half intervals, conversion guaranteed by intermediate value. In bisection, the conversion is always guaranteed, but it's slow and takes multiple iteration for this thing. uh, Bisection method, we have algorithm. If f of a into f of b is greater than 0, then we have the error. uh, then so we calculate c, which is a midpoint of a plus b divided by 2. If mod of c is greater than tolerance, we will return the c, and we'll continue that. And if the f of a dot f of c is less than 0, then we'll substitute b value of b to c, else we will substitute value of a to c, and repetitive until we get the tolerance. The time complexity for the following is order of log 2 log base 2 b minus c divided by tolerance, which is a midpoint of our. And the space complexity for the same is order of 1. The result of conversion is 1.618034 after more than 14 to 20 iterations. The Python code is there for the respective. We use the lambda function and a function for bisection, in which we take input as rf a first the interval a and b and tolerance, and we'll perform by using the loop. The second and third method, we have regular falsi and secant. They both are more alike method, but regular falsi guaranteed us guaranteed conversion, whereas secant does not provide us guaranteed conversion. They both are different in some point. We use secant chord line between a comma f of a and b comma f of b instead of a midpoint. So we create a formula for the midpoint c is equals to a minus f of a dot b minus a divided by f of b minus f of a. While using this formula, we will calculate the iterative method for the same question, and we'll ended up getting 6 iteration, the first 6 iteration for the same. On the other hand, secant method, it used two previous iteration. There is no two initial guesses or range. We will What we will do, we'll initially guess for started with the one point and calculate the respective c for the point, and we will substitute that point for in place of n, and continuously doing that. It does not The initial guess should be much perfect. It does not guarantee you the guarantee conversion. The fourth method we have is Newton-Raphson method, the most effective and efficient method. The geometrical interpretation for the following is: we will draw a line to tangent line to the curve y equals to f of x, and at each iteration, the x of the tangent is the next iterable. It is the most fastest method to find the root of the polynomial. The time complexity for the same is O log n 1 by e, which is our tolerance, and space complexity of order of 1. Conversion for the following equation x square minus x minus 1, we will we will get the conversion at only in 4 iteration, whereas whereas bisection is taking more than 14. We will get only in 4 iteration. We can see in the graph, in the first iteration we will get zero point 0.1, in the second iteration we'll get 1.625, in the third iteration we'll get 1.6180, and in the last we'll get the exact 1.618034. And at last we have fixed point iteration method. This is the non-guaranteed conversion method. uh, it is only valid when g of x square is less than the mod of g dash of x is less than 1, which is the near root. The initial guess should be perfect unless we will not able to find the root for the same. The time complexity for this is order of n, and space complexity is order of 1. Moving on to the next question, we have to perform interpolation for the given data, this, and estimate the value of f of 9. So let's understand the question. We will first use Lagrange interpolation. Using Lagrange interpolation provide us the more effective way. So first of all, we will calculate everything for the each value. We will calculate p of x, which is summation of y and l1x, y1 l1x, where l1x is equals to summation of j is not equal to 0, x minus xj divided by x1 minus j1. We'll perform this and create a table for every Lagrange points. By computing this, we will get the value of different for the same iteration at the different point, and we'll then find yi dot li for 9. After putting this all into the p of x equation, we will obtain the value of f of 9 should be approximately 843. The time complexity for the Lagrange's interpolation is order of n square, and space complexity is of order of n. Then we have Hermite interpolation. This is the much faster interpolation method in compared to Lagrange. Here we will have t equals to 0.5, which is the time, and we will find out the step size, which is x2 minus x1, which is equals to 4, and t equals to 9 minus 7 divided by 4, which is 0.5. We will find Hermite's points h00, h10, h01, h11. After this, we will get the result. We will calculate the result for x equals to 9. We will put this into the p of x in the condition. The formula which is carried out in this interpolation method is p of x equals to h0 h0 into x1 and so on. By calculating this, we're getting the value f of 9, which is approximately 866 for 7, 11. The time complexity of this is order of n square, and space complexity is also order of n square. The third method we use for this interpolation is Newton's divided difference method. In Newton divided difference method, we will create divide difference table. So we have different points of x 5, 7, 11, 13, and 7, and with we have respective f of x for the same. So we have 5 for x equals to 5. We have f of x is 150, 320, 392, 1452, 2366, and 5202. Now we will calculate we will create the difference table by subtracting lower value, higher value to next value to previous value divided by next value to the previous value. So 392 minus 150 divided by 7 minus 5 will result as 121. And with respect to this formula, we will calculate all the divided difference table. And now we will apply to find p of 9, which is we will use forward difference. So we will calculate only these longitudinal values in this to calculate that. Next, we have forward and backward Newton difference. Previously we calculate the difference table. Now using that difference table, we will calculate for the interpolation either Newton forward or Newton backward. So we have respective formula for this. We have y0 plus p of lambda y0 plus p of p minus 1 divided by 2 factorial lambda y2, and so on, where p equals to x minus x0 divided by h, and we will start x is near to the start of the table. For the backward interpolation, we have p of x equals to yn plus s into nabla and on. The third question is numerical differentiation. We have to perform numerical differentiation on the given data. Interpolation is based, so first we use interpolation based and then finite difference based. In this, we have to calculate p dash of 9. We have to find the value at x equals to 9. So for we have four respective formulas for forward difference, for backward difference, for central difference, and for second derivative. We have respective formula here and their accuracy, which is O of h, O of h, O of h square, and O of h square. And we have respective example result, which is f dash of 7, which is approximately 265, f dash of 7 for backward interpolation, which is 121, backward central interpolation for f dash of 11, which is around 329, and f double dash of 11 for second difference, it's 64, which is non-uniform. The time complexity for forward, backward, and difference is order of n, and space complexity is order of 1. The next question we have, the fourth question we have, is numerical quadrature formula. The Newton-Cotes rules, trapezoidal rule, Simpson's 1 by 3 and Simpson's 3 by 8, and Weddle's rule. These all five rules comes under numerical quadratures formulas. First, we have Newton-Cotes rules, general derivation. What we have to perform the integration on a given value by using Newton-Cotes formula. We have to use certain rules to apply these formulas, where Vi is equals to integration 0 to n Lit dot dt. We have certain rules like trapezoidal rules, which consume two nodes, Simpson's 1 by 3 rule, which consumes 3 nodes, Simpson's 3 by 8 rule, which consumes 4 nodes, and Weddle's rule, which consumes 7 nodes. We have different formula for different things. For the trapezoidal, we have h by 2, where h is step size, 1 comma 1. Then we have h divided by 3, which is 1 comma 4 comma 1. 3h divided by 8, 1 comma 3 comma 3 comma 1. And at last we have Weddle's 3h by 10, 1 comma 5 comma 1 comma 6 comma 1 comma 5 comma 1. We have order of error, which is order of h square, order of h to the power 4, order of h to the power 4, and order of h to the power 8, and exact degree as respectively. Trapezoidal is a composite rule where t is equals to h divided by 2, which h is a step size, and will perform the following. The error that could be occur in trapezoidal rule is minus of b minus a h square divided by h. And for the Simpson's 1 by 3 rule, composite and only even quantities are there when R interval is divided into even steps. Then we have Simpson's 3 by 8 rule and Weddle's rule. Simpson's 3 by 8 rule is used when R interval is divided into multiple of 3. Multiple of 3 is such that the single interval, we use the formula 3h by 8, f of x0 plus 3 f of 1, f of 2, f of 3, so on, and it is composite. The error is respectively given. Then we use Weddle rule. Weddle rule is used when R interval is divided into 6 exact points, or we need to divide R system into 7 different points. Here is the Python code for the Simpson and the Weddle rule respectively. Let's move on to the next question. The next question wants us to solve system of linear equation. We have given three equation: x plus 2y plus 3z equals to 14, 3x plus 2y plus z equals to 10, 2x plus 3y plus 2z equals to 14. And we know the solution for this system of equation where x equals to 1, y equals to 2, and z equals to 3. But we are going to solve this system of linear equation by different methods. The first method that we have is Gauss elimination method, which is also known as partial pivoting. In this, we will imagine or structure our equation into matrix format and convert that square matrix into upper triangular method. The steps is first initializing the matrix A dash B. it could be it should be argumental matrix. Then we will pivot column 0 and make horizontally everything 0 by using rows operation. Then we will take pivot as column 1 and pivot using rows operation. We will convert our matrix into upper triangular matrix. After converting upper triangular matrix, we will substitute the values and obtain the value of x, y, z respectively. The time complexity for the Gauss elimination with partial pivoting is order of n cube. For forward elimination or for backward substitution, order of n square, and maybe order of n cube. Again, the space complexity is constant, which is order of n square. The second method we have iterative method, which is also we have a Jacobi method or Gauss-Seidel method. These both method convert our system of equation into matrix and convert that matrix into diagonal matrix. So what are the features it provides? Jacobi provide all at once all the values. Seidel provide immediately new values. Speed, Jacobi is slow. Gauss-Seidel is much faster than Jacobi. Parallelism. It can easily parallelized. Gauss-Seidel cannot be parallelized. It need to be execute sequentially. The time the time complexity that Jacobi has is order of OM square, and Seidel also have OMN square. Conversion condition. Jacobi converts into the diagonal dominance, and Gauss also converted into the diagonal dominance. The sixth question is approximation theory, least square and polynomial approximation. Let's study these. We have S equals to summation y1 minus pxi to the whole square, where p of x equals to a plus bx. We have given the data as following. We have to perform least square linear approximation on the given data. The normal equation we can write is 535, 35, 653, a comma ab is equals to 9562 and 138658. We have converted into the matrix and we compute the sum of the given following and will ended up getting 138658. Solving this normal equation will obtain value of a and b, which is minus 2423 and 409. Linear fit, we'll get the linear fit with the time complexity of order of n into m plus m cube, and space complexity of order of mn. Then we have orthogonal polynomial approximation. This is the most provided approximation method. It avoids ill condition of normal equation. Each coefficient compute independent via inner product. Legendre polynomial and Jacobi polynomial. We have P of 0x, P of P1 substituted. This coefficient acts independently, where on the other hand, it's before fitting, it's all dependent. We have provided with the Python algorithm and code for the respective method. The last question we have is order of differential equation. We have given dy by dx equals to x plus y, where y of 0 is equals to 1. We have to find exact y equals to 2e of x minus x for this equation. So let's solve this. We can solve this by using Euler methods. Euler method state yn plus 1 is equals to yn plus h of f of n f of xn comma yn. The geometrical interpretation is to move along the tangent line at each step for the first order Taylor method. So we have our data 0, 0.2, 0.4, 0.6, 0.8, 0.1. And using Euler methods, we will obtain y of n. Y of n is equal to f of x of n. So for 0, 0 we have 1. For 0.2 we obtain 1.2. For 4 we obtain 1.48. For 0.6 we obtain 1.856. For 0.8 we obtain 2.3472. And for 1 we obtain 2.976. We use this formula yn plus 1 equals to yn plus h of f of n f of x and xy. to obtain these respective values using Euler method. We have given a step size equals to 0.2. The time complexity for the Euler method is order of n and space complexity is order of 1. The observation we had at x equals to 1, Euler gives us 2.9766, which is exactly 3.436. The error we had here is 0.468 for the step size of 0.2. The next method we have Runge-Kutta method for the order of 4. Here we have given h equals to zero point 0.2. Runge-Kutta method. In this method, we will compute k1, k2, k3, k4, and then obtain the value of the next ek1. So here similarly we have given the points point 0, point 0.2, point 4, point 6, point 8, and 1. For this respective x value, we need to calculate yn. Yn is we can define for the yn we need to calculate k1, k2, k3, k4 respectively, and then putting in the formula yn plus 1 equals to yn plus k1 plus 2k2 plus 2k3 plus k4 divided by 6. By using this formula, we can obtain 0.0 and we can obtain the value 1. For 0.2, we can obtain the value 1.24, 2805, and respectively so on. Runge-Kutta method match exact solution to the sixth decimal. Here, using Runge-Kutta method, where we obtain at when x equals to 1, we obtain the value of yn is equals to 3.436563, which is the exact value as well we was given at the beginning. The third, we have Picard method, successive approximation. We convert the integral and we convert the integral equation and iteration y of n plus 1 x is equals to y0 plus integration of 0 to x f of t comma y n t dot dt. We will use this formula by symbolizing f of x comma y is equals to x plus 1. For y0 x we will obtain 1. For y1 x we will obtain 1 plus integration on respectively. Conversion of Taylor series. At x equals to 0.2 will obtain the exact value, which is approximately 1.242733, which is exactly our closest value we obtained. The time complexity for the Picard method is order of n square and space complexity of order of n. The conversion only near x0. Here is the Python code for the same. And at last we have Taylor series, the order of 3. We use higher derivation at each step with the formula yn plus 1 is equals to yn plus h, which is a step size, y dash n plus h square by 2 factorial y double dash of n plus h cube by 3 factorial dot y triple dash of n, and so on. This is the formula we need of the Taylor series, which is modified to solve this ordinary equation. Derivative formula, we will put our values of x in the similar context. We have given step size of 0.2, so we'll compute xn, and with respect to xn we'll compute yn with using Taylor series. Here we can see we are getting the exact value 3.4362, which is required. The time complexity for the Taylor series is order of n into p, which is n is the step size and p is the order of the series, and space complexity of order of 1. So this is all about the ordinary equations. OE method summary comparison. So we can compare all the 4 methods: Euler, Runge-Kutta, order of 4, Picard, and Taylor series, Taylor method. We can clearly see the order for each is 1, 4, variable, and 3. So the most effective is Euler. Most effective is Runge-Kutta here. Global error, the global scope of error for each equation are respectively. And in result, we can understand the exact solution we obtain for the given equation is 3.4366, which is obtained by Runge-Kutta order of 4 method with the minimal error in it, with approximately uh, 10 to the power minus 6, and the most and the method that give us more error is Euler method with the order of 1, which provide us with the error of 0.460. So this is all about assignment 3. Thank you for watching.